Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. And as you know, within this module, we are trying to understand that how does the operating system manage this fundamental hardware resource that we have, that is the CPU, by providing this abstraction of a process, right? And within this second module, we are currently on the fourth topic, that is process system call API. So within this topic, we are now nearing the end, right? And in this topic, we basically wanted to look at all of the important operations that we would like to perform on processes, right? Like process creation, termination, waiting for another process, right? These are the important operations that we would like to perform on processes. And the way to perform these operations is via the system call interface. So in this topic, we looked at the UNIX system call interface to be specific, right? And we have looked at the operations as well as the corresponding system calls that we had. Um, like in summary, we talked about four major system calls. That is fork and exec for process creation, exit for process termination, and wait for process waiting, right? Now in this video, what I want to do is that I want to show you like how using these four major or basic system calls we can construct the UNIX shell, right? So the shell is a user process, just like any other process. It's a simple user process with a special task of interact, like enabling the user to interact with the system via the command line interface. And it is a simple piece of software constructed using these, or at least there could be more system calls, but at the core it works using these four major system calls, right? So let's put all the pieces together and see how we can make the shell using the system calls that we have studied up till now. So let us recall by like looking at all the system calls that we studied in this topic, right? So we had four major operations that we wanted to understand. That is process creation, process termination, waiting, and some miscellaneous system calls, which we will look at in this video in the end, right? So three major operations: creation. For process creation, we had two system calls, fork and exec. These are like counterparts of each other, and you have to use them together to get the best out of the interface, right? Then we have process termination, which has a simple system call of exit, and there is a slightly complex system call, that is the wait system call. The interface is simple, but the function, the overall flow has to be understood properly, right? So these are the four major system calls that we would be talking about, like how they are used to construct the Unix shell, right? So first of all, before I talk about how the shell works using these four system calls, let us quickly recall that how the Unix shell works. So the shell has a basic interface. It has a command prompt, right? And the command prompt is basically waiting for the user to enter the next command, and that command is basically a piece of text written in text, right? Where there is the name of the binary or the executable that you want to execute with some appropriate flags. This is how a Unix shell command looks like. So when you enter that command, the shell executes that command, and only when that command is finished, it goes on to accept the next command. Like if a particular command is in execution and it is running in the foreground, the shell will not accept any other command. There is an exception to this rule, is that if you put that process into the background, then it will accept more commands. But in the normal case about which we will talk, right, in the normal scenario, unless the current command that you have given, unless that has finished, this shell will not move on to the next command. It executes the command in a sequential fashion. It takes a command, executes that, waits until that command finish. Once the command finishes, it goes on to accept the next command. We have talked about this and seen several examples in the previous videos also. So now let's see how the Unix shell works, is built up basically using the four system calls that we talked about. So what happens when you enter a command? When you enter a command, the shell calls the fork system call. And now there are two copies of the shell, right? So let's say this is the parent process, the parent shell, And since the fork system call has been called, right, there will be a duplicate. Basically, there will be a new process which is running an exact same program as the parent process. So there are two copies of the shell running, right? But we do not want to execute the same piece of code. So the next step is to call the uh, exec system call, right? But that is what the child process will do, right? We'll look at it soon. But before the child process replaces the program with the command that you have entered using the exec system call, the parent process, the parent shell process will call wait, right? The parent process needs to wait until the child process finishes execution. So the parent shell process will call wait, and it will put itself to sleep. So the operating system will basically suspend the execution of the shell, the parent process we are talking about, right? And now it will wait until the child process that it has created executes the command that has been given by the user, right? So now let's shift our attention to the child process. So what does the child process do? It will change its program via the exec system call. And let us assume, right, for the sake of this example, that the command that the user has given on the command prompt is the ls command. As we know, the ls command is used to list out the contents of the current directory, the files and directories that are part of the current directory, that will be listed by the ls command, right? So you can see we have the three system calls already called. So the child process has called exec and replaced its program with a new program, which is basically the command that was entered by the user. And soon this command will be finished. It doesn't take a lot of time, right? A few milliseconds to execute this command. If the command could be something like a long running command, if you enter a sleep command, or you are downloading some file from the internet or installing something, then it would take some considerable amount of time. Otherwise, in most cases, the command will finish instantly. But nonetheless, however is the waiting time, the parent process which had been put to sleep will wait for the current command to finish, right? And when the current command finishes, it will request termination using the exit system call. But before that, let me also talk about why there is we have talked about this, like, but let me also recall that why we have the two system calls for process creation, right? So for fork and exec, right? So why do we have separation of fork and exec? So basically, why is like we have a separate call for fork, that creates a new process, and the call that replaces the current program with a new program, that is exec. Why is that separate from fork? So the reason is that it allows the shell to change the environment of the child process before executing the child process, before calling exec, right? It could have very well been that fork and exec, the functionality of fork and exec would be put together into one system call, right? There could be one single system call that would create a new process and execute a new program. But in the Unix interface, things are not this way. In the Unix interface, there is a separation of concern. The system call for creation of a new process, that just creates a copy, nothing else. It just creates a copy of the original process, is the fork system call, which is separate from exec. The exec system call, which allows us to execute new programs, right? That is replace the current program with a new one, that is separate from fork. And as I said, the rationale behind this design is that before calling exec, we basically have a chance to alter the environment of the child process that we are about to execute. And this allows us for several useful features, like in the Unix shell, like output redirection, the concept of pipes, right? I have talked about this in a previous video where we talked about the difference between fork and exec. So in output redirection, what we do is that instead of like sending the output to the screen, we can send the output to a file, right? That is output redirection, either the standard output or the standard error. You can divert that into a file. So before calling exec, all you have to do, the shell will do this for you, right? You will give the appropriate command on the command line for output redirection. The shell, what it does is that it will close the default standard output and error channels, and then it will connect them with that of a file handle. So that is the way, by altering the environment before executing the new child process, we can have useful features that I just described, that is output redirection. The output will go to the file instead of the console. and this can be useful when the logs are needed for some future in future, right? And the other concept that I talked, that is pipes. In pipes you can like communicate two processes. This allows inter-process communication. The output of one process can become the input of another, right? And in this way we can chain a series of commands, right? For example, you can like write, like give the command to get the history of shell commands, and then use a pipe operator, and then use the grep command to search for a specific uh, piece of text in the history of commands, right? History, pipe operator, grep, and then some piece of text. This allows you to search for a specific command that you had searched in the past, right? This is one of the examples, right? I have talked about similar examples in that video, right? So this is where the output of one process is becoming the input of another. So we are combining the functionality of one binary with that of another. So I talked about two important features of the Unix shell. One is output redirection, and the other is the concept of pipes. So all of these are enabled, or we can say these features are made possible because of the separation of these system calls, fork and exec. If fork and exec would have been one single system call, then it would have been difficult to alter the environment and enable these features. You need to alter the environment. You need to like change the output. Either you can connect it to a file or you want to connect it to a process, right? So that altering of environment can only take place if we have a separate fork and a separate exec. That is what we have in the Unix shell. So this was one point that I wanted to recall, right? So let's come back to our example. So let me again recall what just happened, right? We have been talking about this altering of environment. So we started with the shell, and then the shell, basically we wanted to understand what happens when we enter a command on the command line. When we enter a command on the command line, the shell basically calls fork, and then it creates a new process for the command that we want to execute, and it itself calls wait system call to go to sleep, right? And then the child process that the shell has created, it will call exec to execute the command that we have given. And then we talked about why there is a separation of fork and exec. That is, before, just before executing the command that the user has given, we can change the environment, right? And now what happens? The child process that the shell created for executing the command that the user has entered, that will eventually finish, right? It will call the exit system call and it will terminate. And once the child process terminates, the one which had been executing our command, once that terminates, the shell, which is the parent process, which had been put to sleep by the operating system since it had called the wait system call, now it will come back, it will resume the execution, right? And then it is ready to execute the next command, right? So this is the whole cycle, right? We had the shell, it calls fork, the shell itself goes to wait, like sleep, by calling wait, and then the child process calls exec to execute a different command. It exits, and when it exits, the shell which had been suspended, it comes back, it resumes execution, and on this loop, you can say, goes on. This is how we are able to execute a sequence of commands on the Unix shell. And you can see this is something which you can also build, right? The Unix shell is a simple program, right? A user space program. There is nothing as such that is in the kernel, like in the kernel space. It is all in the user space. We talked about two levels of when we are executing. There are two levels, right? One is the kernel mode, and one is the user mode. There is code in the kernel space, then there is code in the user space. What I'm saying is that the shell, although it is very much close to the kernel, all of its code is in the user space, right? And it is built using the system call interface, and it is something that you can also build for yourself. You can build your own shell, right? So this is how the Unix shell works, and you can see how all of the system calls that we studied till now, they are put together, and you can see all of them working together to build the Unix shell. Right now we will discuss the timeline flow in a more diagrammatic way, right? Let's see that next. So now let us see the same thing, that is the working of the Unix shell, but this time we'll see a timeline diagram that will help us to understand and visualize things in a better way, right? So in this diagram, as you can see, there are four parts. That at the very bottom, there is the kernel, right, shown in red color. And this is the interface between the kernel and user space processes, right? everything in the blue is basically executed in the user mode without any privileges, right? And everything in the red will be executing, that is the kernel code will be executing in the kernel mode. And within the user space, again, you can see there are three parts. I have one band for the shell, then one track for the command that we want to execute. In this case, the ls, it could be any user command, right? So we have two tracks for user processes and one track for the C library, right? Just above the kernel, there is a library, and over on top of the library, we have the user applications. So this is the shell, right? So it let's now assume that the user has given some command to execute, right? So let's see what happens next. So when the user gives a command, the first thing that the shell does, as we discussed, is that it calls the fork system call, right? This transition is saying that the control is going inside the kernel. This is the fork system call being executed, and it comes back, and there will be a new process. The child process that we saw will be a copy of the shell process. I have not shown the child process yet, but there will be a child process that is created by the kernel, right? Now, so there are two possibilities. One thing is that the child process can also start execution. So here when we call fork, it can very well be the case that we return into the child process, right? Even then, at some point in time, the shell will get its, we'll see the simple case first, right? In the simple case, we'll first sleep, right? We'll call the wait system call before the child process starts execution. That timeline diagram is simpler to understand. So let's first see that. So now let's assume that the shell process gets the control of the CPU and not the child process. And then it goes back into the user space, and then it invokes the wait system call and suspends its execution. This black dot that you see, I'm using this to signify that there is a context switch. There is a switch from one process to another, right? And to which process we are switching to? We are switching to the child process that we just created, right? So at this point, it is executing the shell code, right? Although this is the ls process, but at this point, it is executing the shell code only, right? Now, to change the code that it has to execute the actual command that has been given at the command line, we'll call the exec system call, right? And once the exec system call is done, we return into the C library, right? So all of the returns will go through the C library, but here I am focusing because I wanted to also show the startup function, right? So all of these parts are going through the C library, right? But here I'm focusing more on what is happening inside the C library, because here we have the startup function, which will call the main function. So the C library, the C runtime has this function which accepts the arguments that you pass to the exec system call and passes to the main function. All of the stack is created and initialization is done and preparation is done so that the main function call, the main body, can be called. And let's see what happens next. The startup function in the C library calls the main function, and main function is where all of your work that you actually want to do will happen. So this is the ls command. So this is where the basically listing out the directories and the files within a given directory will happen. So this is the main function. This is the main part where the actual task is getting done. Once that happens, we return back to the startup function, and in the startup function, we will do the tear down, or basically, we will now call the exit system call, right? We are now kind of finishing up what we started, right? So here we call the exit system call, and once we call the exit system call, the control goes back to the kernel, right? And inside the kernel, we basically, now the process will be kind of, this ls process will be terminated. It will no longer exist, right? Once it has called exit, all of its resources would be deallocated. Only its what to say, the process control block will remain in the system. Briefly, in zombie state, we have talked about this in the previous video, because it contains the exit code of the child process, right? So when we call exit, the ls process will be terminated, all of its resources will be deallocated, and just its process control block will remain in the system for a brief while, right, in zombie state, because it contains the exit information, the exit status of the ls process, right? And now here we again have a switch. Since the ls process is done, we have to execute, or we have to go back to some other process, and we assume that we're going back to the shell process, right? And while going back to the shell process, let's go back to where the shell process was. So shell process called the wait system call, and at this point it got switched out. At this point it lost, or you can say it gave up the control of the CPU. Right, between this dot and this dot, in this timeline the child process was executing. It called exec, it executed the main function, and then it called exit. So now between this dot and this dot, our child process was executing, and now it's time to go back to the shell process. So since one of its child process has terminated, the wait system call will return, right? The operating system will wake up the shell process which had been suspended, right? Since one of its child process has terminated, and the wait system call will collect the exit status of the ls process, the child process, deallocate its process control block, and that zombie process, right, the process control block that was there, that will also be cleared up. And then we will finally return to the shell process in the user space, and where the shell can inspect the exit code and take appropriate action. So this is the flow of the shell process, right? How it creates a new process, and then it goes to wait, the new process executes, right? And again we return back to the shell. So this is the whole timeline. We saw it in a, like, in a timeline diagram. So I was also talking about the case when the child process goes first instead of the shell process calling wait. That can also happen, right? So when the shell process calls fork, right, at this point we can very well have this context switch at this point, right? I'm just discussing the two different possibilities. We have also talked about these two different flows in the wait system call video. Either the child process can go first and then the parent can go, or the parent process can go first and then the child process can go. We discussed this case when the child, when after the fork system call, the parent process is going first, calling the wait, sleeping politely, right? What if the child process goes first? I don't have the diagram, but even then, if the child process goes first after this fork system call, it will do the same things. It will call exec, it will call main function. If for any reason in between the control is given to the shell, or even after the child process exits, the control will go back to the shell, the same thing will happen. The shell will call wait. If the only thing that you need to remember is that if the child process has exited before the shell process calls wait, the child process will remain in the zombie state. The shell process will call wait and clear up that zombie process. If the child process has not terminated, the shell process again, it will call wait, but this time it will suspend its execution. This is the flow that we already saw. But if it so happens that the child process goes first and it finishes execution before the parent process, the shell process calls wait, in that case the shell process will call wait because it's in the flow, but it will not suspend its execution, it will return immediately, right? So that was a minor detail, right? But the overall concept that you have to understand is that there is fork for creation of a new process, waiting that the shell will use to wait on the child process. The child process, since it's a duplicate, has to change the program, execute the program, and exit. And when it exits, the control is given back to the shell process. The order in which the child or the parent execute after fork, that is just a detail. And in any case, whatever happens, if parent goes first, it will sleep and child will execute. If child goes first, it will execute, and parent, when parent is resumed, it will return immediately from wait. That is a minor detail, right? But this gives you a basic idea, right, of how the shell is constructed using the four basic system calls that we have. There will be definitely more system calls in the shell, right? The shell is a more complicated piece of software. There is whole bunch of like features, like signaling mechanism is there, right? The full functioning shell will have more system calls, but you see the basic functionality of the shell is to accept a user command and execute that command, and then go on, keep on doing this. The basic core of the shell can be constructed using these four system calls, right? And now in the end of, like, we are moving towards the end of this video. In the last section, we'll go over the miscellaneous system calls that we mentioned that we will talk about. So I'm only going to talk about two miscellaneous system calls, the get PID and the kill system call. So let's quickly look at these two system calls. I'll go through these system calls at a high level, not in much detail, but even then that will give you an idea, right? So let's understand these two system calls. So let's first talk about the get PID system call. It's a very simple system call, and we have looked at it in the previous videos also. I'll just go over quickly. So the get PID, as the name suggests, it returns the process ID of the calling process, right? You can see it returns a process ID. It does not take any argument, right? So with every process in the system, we have a unique integer assigned to it, which helps the computer system to identify it, right? And that process ID is returned by this get PID system call, right? So whenever a calling process invokes the system call, its own PID will be returned. So let's quickly see the flow. Let's say we have a process A, it calls the get PID system call, right? So what happens is that, let's say this is the process control block for this process A, and within the process control block, we store this process ID information. And let's just assume that the process ID of this process is 200. So the get PID simple call is very simple. All it will do is that it will return the PID that is 200. That is all there is to the get PID system call. So now we are going to talk about the last system call in this topic, that is the kill system call. So the kill system call, as you can see, can be used to send any signal to any process. So a signal, like in real life, is a way to communicate, right? A person can send a signal to another one, right? So in the same way, signals in the computer system are used for inter-process communication. Each signal has a different meaning, a different behavior, right? Basically, when there is a signal, then there is some kind of action, right? And depending on the signal, we have variety of signals in the Unix system call. Different actions take place. This is a way for processes to communicate with one another. One process can send a signal to another to take a certain action, right? So this is a method of communication. So what is the kill system call? As we can see, the kill system call can be used to send any signal to any process, right? So how does the interface look like? So basically, we take a process ID, right? This is the process ID of the process to which the signal has to be sent, right? So first of all, you identify, right? A process has to identify to which other process we want to send a signal, and for that we need a process ID, right? And that process ID has to be supplied here. A process ID, as we just discussed, is a way to uniquely identify a process in a given computer system. So once you have identified your process, the next step is to send the signal. And for every signal, we have an integer to signify that signal, right? So we can see an integer representing the signal. We'll soon see the list of signals that are supported on Linux, and each of them is assigned a unique integer. That unique integer is a way to identify that signal. So we are saying to this process ID, basically to the process with this process ID, send the signal with this number, right? And once the signal is sent, what is the return value? On success, if the signal was sent, right, 0 is returned. On error, -1 is returned. Very simple, right? If the sending of the signal was successful, then the kill system call will return 0. Otherwise -1 will be returned. So let's look at some examples of how the signals look like, and how does the kill system call behave. One small thing that I wanted to talk about before we see the examples is that why is the skill system call named as such? I described that the function of the kill system call is to allow a process to send a signal to another process, but the naming is like it says it is like killing another process. Why is the name assigned as kill, but the functioning is that we can send any generic signal to another process? So the reason is that you can look up it in the internet. The reason is that when the kill system call was introduced, at that time it was just it had only one signal, right? And its job was to kill the target process. Over time, with newer versions of Unix, more and more signals got introduced into this mechanism, and not every signal was meant to terminate. The newer signals that were added, they had other functionalities also, but the naming has remained, right? Originally it was used to kill the target process. Over time, more and more signals got added, right? But the naming has remained. So the functionality of the kill system call is to send any signal to any process, and only few signals are used to kill the other process. Rest of them have other functionality. It's just about legacy naming, right? So having discussed about the naming, let's see some signals. So this is taken from the man page. You can visit the man page yourself and look it up. So each of this signal has been given some kind of name, right? And on different architectures, they have a different number, right? For example, let's see, we'll see three examples: sig term, sig count, and sig stop. So the sig term signal is used to terminate the process, right? And it has the same number on all of the architectures. Then there is a sig stop signal that is used to stop one process. When I say stop, it does not kill a process. It is like pausing a process. You can pause a process for some time. And on different architectures, you can see on different hardware architectures, the number that is assigned to the signal is different. On x86 and ARM, it's 19. On Alpha and Spark, it is 17, and so on. And the counterpart of the sync stop signal is the sync con signal. So sync con signal is to like allowing a process which has been paused to continue. Either you can pause a process using sync stop, or you can resume the process using sync continue, sync con, right? So this was the brief description of the signals that we have on Unix. There are so many signals that you can go to the man page and look up what each of these signals do. So, but we'll discuss the easy ones that are easy ones to understand. Let's start and see the three signals that we talked about. Let's take an example. Let's say we have two processes, process A and process B, and this is the operating system. So process A wants to send a signal to process B. So what does it do? It wants to request the operating system to send a signal to process B. It will use the kill system call, right? So let's say it wants to pause the process B, right? Process A just wants to pause process B for some time. So what can it do? It, let's say process B has a PID of 200, and it can use the six stop. This is an integer. I'm just using the naming. As you can see, each of these signals has been assigned a name, but it is essentially a integer, right? So process A can use the kill system call, give the process ID of process B, and use the six stop signal to pause this process. So what does it do? It requests the operating system to send a signal to pause process B. So this will pause the or halt the execution for some time of process B. So obviously one important thing is that process A must have the permissions to send the signal. Either it should be a parent process or process within the same group. Whatever rules are being followed for permissions, it must have the authorization to pause a different process, because it's a kind of crucial thing you're doing. You're kind of pausing another process. So you must have the authorization to do so, right? So we're assuming that authorization is not the issue here, right? That a process A has the necessary permissions to send like signals to process B. Then if a process sends a signal to pause another process, it can also send a signal to like signal the other process to resume execution. So for that we have the signal siccon that we just described. So when this is what the process A calls, this is asking the operating system to send a signal to resume process B. And similarly, if the process A has necessary permissions, it can also terminate process B. So for termination, the signal that we have to use is sigterm. So let us see a concrete example, right? Let us see this C code and see all of the signals, three signals that we talked about in one piece of code. So let's go to the piece of code. Let's first of all understand what is happening here. So there is this main function, right? So in the main function, we are calling the fork system call, right? So this process will create a copy. There will be a parent, there will be a child. Within the child process, where we return process ID 0, as we know, the fork system call returns twice, once in the parent and once in the child. In the child, it returns the value of process ID as 0, right? And so the if part will be executed by the child process, and the else part will be executed by the parent process. So what we are doing in the child process, there is an infinite loop while one, it is just printing that child process is running, and then it is sleeping for 1 second. So we are printing a statement and then sleeping, and we are doing this infinitely in a while loop. So this is what the child process is doing. Next, in the parent process, we are sleeping for 5 seconds, then sending a signal to the child process to pause it, right? We have stored the process ID, right? We have stored the process ID, and we're using this process ID to send signals. Once we are sending the six stop will basically pause the child process after 5 seconds. So we are sleeping, right? After 5 seconds, the six stop will be sent. So the child process will be executing in the first 5 seconds, then it will be paused, and then for 5 seconds we are sleeping in the parent process. So for the next 5 seconds nothing will happen, right? The parent is also sleeping, and the child process has been paused using the six stop signal. Then the parent process sends a sig continue, so now the child process will start running again, and then it sleeps for 5 seconds. So in the last 5 seconds, the child process will again be running. And finally, after 15 seconds, we are sending a sig terminate signal to the child process, which will terminate its execution. So what should be how will the overall flow look like? I recommend that you stop the video and think it through, and then we can you can verify the output. So I'll go on and execute this piece of code, right? I've already compiled this skill program. So you can see the child process starts running. It will print this statement 5 times because we are sleeping, right, for 1 second in the child process and printing. In the first 5 seconds, the child parent process is sleeping. Then it sends this 6 stop signal. So during that time, as you observed, the child process was not doing anything. And after 5 seconds, the second 5 seconds, total of 10 seconds, it again sent a signal of continue to the child process, right? So child process started again and printed the statements 5 times, right? And then in the end, it terminated. So I'll run it again. For the first 5 seconds, the child process is running. Then it gets halted exactly at the fifth second. For 5 seconds, nobody is doing anything. Parent is sleeping. Child was also halted. Then at the 10th second, it resumes execution. And for the next 5 seconds, still from 10th to 15th, the child process is running and printing the statement. Finally, at 15th second, the parent process sends a terminate signal to the child process and kills it. Right. So this is how all of the signals we discussed. We took an example and understood how all of them work. So this is how one process can communicate with another process, right? So the signals are a good mechanism for one process to communicate with other. One process can like do a whole bunch of stuff with the signals. We saw how the parent process was able to pause another process, then make it continue, and after some time it killed it, right? So this is how signals are very useful for inter-process communication. So guys, this was it for this video. In this video, we discussed how all of the system calls, fork, exec, exit, and wait, the four basic system calls that we studied throughout this topic, can be put together to construct the Unix shell, right? We understood the functioning of the Unix shell, like how at the very basic level it can be made, right? And finally, we talked about some miscellaneous system calls, the get PID, the very simple system call which returns the PID of the process. And then we looked at the kill system call, which one process can use to send signals to another, right? So guys, this was it for this video. Thank you very much for watching. I'll see you in the next video. Thank you.